So welcome to the final and third part of the three-phase balance fault analysis video. In the second part, I promised that I will demonstrate two more balance fault example by applying the same fault value that is happening at the other two buses, which are bus 1 and 2. So let us all begin by looking at what and how are we going to analyze the network when we have a balance fault happening at bus 2 as shown over here in this network here. So when we introduce a fault at bus 2, it is similar to connecting the impedance of the fault at bus 2, and that will cause the current flowing in the directions from bus 2 to the ground as shown. Due to the directions of the fault current, we are also introducing the voltage source with the polarity arrangement in this manner. And we also have to switch off all our independent sources, such as our generator and transformer, because we are going to apply the Thevenin theorem and determine what is the Thevenin resistance by looking into the network from bus 2. So when the generators and the transformer are switched off, they become short circuit because they are voltage sources. And when that happens, their impedance becomes series, and we can simplify them as such. Okay, and this is happening also in this branch. So now we are ready to simplify the impedance of the network for this portion here. And we observe that these two branches are in series because bus 3 is in between them. It doesn't affect the connection between these two impedance, as there are no any other element that is connected down from bus 3. So therefore, these two branches can be connected in series, which are in parallel with 0.8J, and they can be simplified into this. And then the summations of these two series impedance is in parallel with this impedance, and they can be simplified further into this value. So this simplified power network shows that VTH is in series with these two impedance, 0.24J and 0.16J. And with that, we can simply determine what is the values of the I2F by taking VTH dividing by the total impedance of the network. And I will obtain negative 2.5J for I2F. And notice that the negative value is due to the divisions of the J value over here. So just now I worked my way from this bigger network into this smaller network and obtain I2F. With that, I want to determine now what is the values of the fault current flowing in each of the independent branches over here. So to do that, I work my way backward instead by decoupling the bigger impedance into their smaller branches that we had initially. So we observe that this 0.24J is actually the summations of these two parallel branches, okay, given to me by these two red arrow. As such, the I2F also has to be splitted into these two parallel branches. To do that, we apply the current divider rule, and we obtain negative 1J and negative 1.5J for these two fault current respectively. And remember that the fault current that we have obtained represent also the change of the current in each of the branch. Okay, the reason is the initial condition when there is no fault happening. Okay, at bus 2, there is no current flowing in each of the branch. So when we compare the fault current flowing after fault happened with no current flowing before fault happened, the fault current also represents the change of the current in the branch of the network. So the change of the current is also delta I. So with that, we are ready to determine what is the change of the voltage, which is delta V in each of the bus. If we are calculating the voltage drop based on delta I, then the voltage drop that we have calculated also represents delta V, okay, which is our change of the voltage. So to determine delta V1, I simply take the voltage drop along this branch. So from bus 1 to ground. So because the voltage drop are defined as from bus 1 to ground, which is in the opposite directions of the fault current, I have to switch the polarity of the fault current in this branch from negative 1J to positive 1J multiply 0.2J. And that is how I obtain these equations and obtain also delta V1. Applying the same logic over here to bus 2, you observe that there are two ways, yeah, you can determine delta V2, either looking into this or this branch. So if I look at this branch, which is a simpler manner, I simply take delta V2 equals to the voltage drop in this branch from bus 2 to ground. So because the voltage drop direction is from bus 2 to ground and in the opposite direction of the fault current, I switch the polarity of this fault from negative 1.5J to positive 1.5J as such, and multiply 0.4J, okay, and I obtain delta V2 as negative 0.6 per unit. Another way of determining delta V2 is by looking into this branch. So to do that, I simply have to determine as well the voltage drop along the branch over here. So I start by walking down from bus 2 to the ground. So as I walk, I will meet negative VTH. So I write negative VTH plus the voltage drop in this impedance, which is I2F multiply 0.16J. And this is what I get. And this is the delta V2. Observe that no matter which branch you are looking at, you should obtain the same delta V2 value. And that is a proof that you have applied your circuit analysis properly. Yeah. Next, we also need to determine delta V3 by looking into the voltage drop of this or this branch. And to determine the voltage drop in these two branches, we need to determine what is the fault current flowing. So initially, the fault current is flowing in these directions. And if the fault current is flowing in these directions and this branch is the parallel summations of these two branches, then I can apply the same current divider rule as well. And the current divider rule shows that the current flowing in these two smaller branches is actually equals to the divisions of the current flowing in this branch by 2, okay, due to the values of the impedance. So if I go ahead and define the voltage drop in this branch between 1 and 3 as in the directions of bus 3 to bus 1, then I will write my equation as such. Delta V3 minus delta V1 equals to the current flowing from bus 3 to bus 1 multiply 0.4J. Because the current is in the opposite directions of the fault current, I also have to switch the polarity of the fault current from negative to positive as such. And then the delta V1 will be the value I obtained previously, and then I substitute the value and I obtain delta V3 as negative 0.4 PU per unit. Another way of determining delta V3 is by looking into this branch, and just to demonstrate, it doesn't matter which voltage drop directions that I'm considering. Let's say that when determining the voltage drop of when determining delta V3 in this branch, I am going to purposely define the directions of the voltage drop as in the directions of the fault current, okay, which is from bus 3 to bus 2. So if I go ahead and do that kind of analysis, I will say that delta V3 minus delta V2 equals to the fault current flowing from bus 3 to bus 2 multiply 0.4J, which I don't have to flip or switch the polarity of the current anymore because the voltage drop direction is in the directions of the fault current flowing, okay, from bus 3 to bus 2. So I go ahead and write negative J over 2 multiply 0.4J. So the division 2 here, be reminded that it is due to the current divider rule. Yeah, the negative and the positive over here is due to the definitions of the voltage drop or the considerations of the voltage drop directions that we are looking at the moment. So no matter which branch that I'm looking at, either in this branch or in this branch, and no matter how I define my voltage drop directions, whether it's from bus 3 to bus 1, or bus 1 to bus 3, or bus 3 to bus 2, or bus 3 to bus 2, or bus 2 to bus 3, as long as the definitions of the current flow is in line and consistent, okay, with the directions of the initial fault current that we have obtained, such as this red arrow over here, you will notice that the delta V3 that you have obtained are the same, yeah, no matter which manner you are calculating your delta V3 with. Okay, So they should have the same value. They are negative 0.4 per unit. So with the values of delta V in all the buses, I can now determine the final V of all the buses simply by taking the initial voltage plus the delta V of them, and I will get the final V of all the buses. The final V of all the buses can be used to determine the current flowing in between the buses by taking the potential difference between the buses divided by the impedance in between them. And these are the current or the final current due to the fault happening at bus 2. And just now we demonstrated the fault that is happening at bus 2. Now we're going to demonstrate the analysis of a fault happening at bus 1. So similarly, fault happening at bus 1, you have fault current in these directions, and then you have the voltage source of the fault, and then you switch off all the independent sources, and then you want to simplify the impedance over here. And as you do that, you notice that these two smaller branches are in series because bus 3 is just a passing bus without affecting the connections of these two smaller branches. The reason is they are nothing, connecting downwards from bus 3. So these two smaller branches can be summed up and in parallel with 0.8J and be simplified to this value. These two branches can be summed up because they are in series and they are in parallel with this branch and be simplified into this value. So this series circuit can be analyzed further and found that I1F as negative 3.125J. So similarly, we want to work backward right now, given that we have known our I1F. So we break our bigger impedance value into two parallel branches, and similarly our I1F has to be divided into these two parallel branches by applying the current divider rule, similarly in the previous example. And these are the values of the fault current in these two branches, and the red arrow represents the directions of the fault current. So to determine now the delta of the voltage in each of the bus, because fault current also represents the delta of the I in each of the branch, we have two manners or two ways of determining our delta V1. First of all, the simpler way is by looking from bus 1 to the ground. So if I define my voltage directions from bus 1 to ground, which is in the opposite directions of the fault current, then I take 2.5J instead of negative, multiply 0.2J, and then I will obtain delta V1. Another way is to look into this branch of the network to determine delta V1. So if I walk down, I will obtain negative VTH plus ZF multiply I1F to obtain the potential drop in this impedance, and this is the resultant delta V1. So no matter which manner of calculating delta V1, you should observe that they are the same. Negative 0.5 per unit. Applying the same concept into determining delta V2, I simply take delta V2 equals to the current flowing from bus 2 to ground multiply 0.4J. So the current is positive 0.625J, okay? Such as this. So for the sake of exercising your circuit analysis, you can try to determine what is the delta V2 by comparing delta V2 with delta V1 and determine what is the voltage drop along their branch to determine delta V2. And you should obtain a negative 0.25 per unit as well. And then we are also going to determine delta V3 by or this branch. Okay, if you decide to look into this branch, and I define that the voltage drop direction is from bus 2 to bus 3, then I take V2 minus V3 multiply IF, or the fault current from bus 2 to bus 3 with this impedance, such as this one. Okay, and then I simplify, and then I will obtain negative 0.375. If I decide to determine delta V3, okay, by taking the potential drop from bus 3 to bus 1, then I take V3 minus V1 equals to the fault current flowing in this branch multiply 0.4J, such as this one. Okay, and then I simplify, and then I will get the same value as well. So notice that this branch is the summation of these two parallel branches, and therefore the fault current flowing in this branch should be split into these two branches as well according to the current divider rule. So with the delta V in bus 1, bus 2, and bus 3 obtained, I can determine the final V of the buses as such. And then with the final V obtained, I can determine also the current flowing in between them as such, similarly to what we have shown in the first two examples. So with that, we have concluded the calculations of a three-phase balance fault. And this is the end of this video series. And if you are still not familiar with the Thevenin theorem, I strongly recommend that you revise and exercise your Thevenin theorem based on the concept that you have learned in circuit analysis. And thank you for listening, and I hope to see you in the third video series where we will talk about unbalanced fault analysis.